Did we already start recording?
Yes, we did. Let's
Oh, sure. Yeah. All
so
right.
welcome back to Nick's Algebraics. Today, my special guests are Random Guy.
The one and only. He found me off the street. I'm random. He said, "You want to make some math videos?" I said, "Sure." And here I am.
That's absolutely right. And we also have Peanut Butter Brother.
What's up, guys? I'm about to eat some very delicious, yummy, healthy food. So don't mind if you hear a little bit of like smacking, a little bit of like groaning, then it's just me eating my food. Okay.
Incredible. And last but not least, we have Ziggle.
Was good. Come from the planet Ziggle. I'm a Zigglite.
Wonderful. As usual, the guided notes will be in the description, so you guys can all follow along. Today, I'm going to talk about the effects elementary row and column operations have on the value of a determinant. All right, so let's do a little warm-up example.
Wait. Before that, are you going to explain conceptually what a determinant is, or are we just going to jump straight into doing determinants?
We're going to jump straight into determinants.
Who are you, and what did you do with Nick?
Mace.
We're not going to spend the first half hour just like talking about the conceptual meaning, the graphical interpretation.
If you're watching this video, I'm assuming you already know how to find the determinant of a matrix. That's like a prerequisite to this video. You should know about cofactor expansion. And now we're going to use elementary row and column operations as a shortcut to find the value of a determinant.
You even have like an original video on how to make how to do determinants, or are we jumping straight into? Oh, you should know this.
I do not have a video on how to find determinants using cofactor expansions.
I don't understand the order in which we do these topics, but that's okay.
All right. So for the first example, we need to find the determinant of matrices A, B, C, and D. So let's find the determinant of A. So does anyone know how to find the determinant of a 2 by 2 matrix?
There is a formula for that. AD minus BC.
Yeah, so this is A, B, C, D. The determinant of A is going to be AD minus BC. All right, that's how it works. So pretty simple. So we're going to do 2 times 5 minus -1 times 6. All right, so 2 times 5 is 10. And we have minus -6 right here. So that's plus 6. And 10 plus 6 is what, guys?
Oh, come on.
16.
21, 21.
You expect
Nine
them
was
to
10.
factor expansion, but you don't expect them to
Oh yeah,
add into arithmetic.
Yes, 16, guys. Good job. The determinant.
That's how old Greasehole's first girlfriend was.
Ooh, I was tired.
So that's a determinant of this matrix is 16. Let's find the determinant of this matrix now. So notice how the matrix B is obtained from A by interchanging the rows of A. So if I swap these two rows, you get this matrix B. And let's see what the determinant of this matrix is. So it's the same idea. We're going to do 6 times -1 minus
10.
Yeah, minus 5 times 2. This equals -6 and then minus 10 right here. So you get -16.
Nick truly right all the steps.
I try. So what do you guys notice happened to the determinant when I interchanged the rows of A?
It was the inverse.
When you change those of A, it became the inverse, so like it became negative.
The opposite, I think, is the word.
Yeah, not
The opposite is. Okay, my bad.
Yeah, no, I was just testing you. It was so Ziggle actually got that completely wrong, and it wasn't me. It was only Ziggle. So
it's the opposite of Greasehole's first girlfriend's age.
What? Excuse me, sir?
It's okay when the says it, but it's not okay when I say it.
That's some prejudice.
Ziggle prejudice.
Yeah, so you get the opposite. When you interchange the two rows of A, that changes the sign of the determinant because it's now -16. So this is the negative of the determinant of A. Okay, that's interesting. Let's look at matrix C now. So matrix C is obtained from A by adding -3 times the first row of A to the second row of A. All right, you can see like if you do this row times -3, this becomes -6, this becomes +3. And when you add that to the second row, -6 plus 6, that's 0. And then 3 plus 5, that's 8. So you get 0, 8 in the second row. And the first row stays the same. All right, so let's find the determinant of this matrix. So this one's easy. So
16.
yeah, 2 times 8 is 16. And then,
Done.
yeah, minus -1 times 0, which is just -0. So you just get 16. And how does that relate to the determinant of matrix A?
It's the same.
It's the same thing. Yeah, they're equal. So this equals the determinant of A. So it looks like adding -3 times the first row of A to the second row does not change its determinant. So that's interesting. Let's look at matrix D now. So matrix D is obtained from A by multiplying the first row of A by 2. So you can see the first row of A is 2, -1. And the first row of D is double that. It's 4, -2. So let's find the determinant of D. So it's going to be 4 times 5. So that's 20 minus 6 times -2, which is -12. And that double negative becomes a positive. So 20 plus 12, that's 32. So
Interesting. That is twice A. Determinant of A, that is.
yeah, this is 2 times the determinant of A, because remember the determinant of A was 16 and now you're getting 32. So that's also interesting. Multiplying the first row of A by 2 multiplies its determinant by 2. This brings us to this theorem here that generalizes these observations. So let A and B be square matrices. So when B is obtained from A by interchanging 2 rows or columns of A, then the determinant of B equals the negative of the determinant of A. All right, so interchanging 2 rows is going to change the sign of its determinant. And when B is obtained from A by adding a multiple of a row or column of A to another row or column of A, then the determinant of B equals the determinant of A. So adding a multiple of one row to another row doesn't change the determinant. And you can say the same thing about columns. Adding a multiple of one column to another column will also not change the determinant at all. And lastly, when B is obtained from A by multiplying a row or column of A by a non-zero constant C, then that means the determinant of B will equal C times the determinant of A. That property right here, property 3, is interesting because it's basically telling you that if I want to find the determinant of like 2, 2, 7, 3, then I can just factor out the 2 from the first row. I can write it as 2 times the determinant of 1, 1, 7, 3, like that. So this third property here enables you to factor out a number from a row pretty much. All right, so let's do example 2 using what we just learned. We want to find the determinant of a 4x4 matrix.
It should be very good.
Yes, this is going to be very interesting. So we're avoiding cofactor expansion and we're going to use these row operation or column operation shortcuts now. I'm going to start.
We're skipping 3x3s.
Yeah, we're going to start off with a 4x4. So
Crazy.
So I'm going to start off by swapping the first and the second rows. So row 1, swap it with row 2. So you're going to get this. So I just swapped the first and the second rows, and you get this. And what do I need to do when I interchange 2 rows? How is this determinant different from this determinant?
You just swapped 1 and 2.
Yeah, and what does that do to the determinant?
You just take the opposite.
Yeah, so I need to introduce a negative factor here, like that. So there's a negative in front of this determinant. All right, because I swapped the 2 rows. Basically, this determinant is now the opposite of this determinant right here.
I see.
Yeah. So here's where the magic happens. This is the determinant of what kind of matrix. If this were a matrix right here, what kind of matrix would it be?
4 by 4, but I'm guessing that's not the answer you want.
Yeah, that's not the answer. I mean, yes, it's a 4 by 4 if it were a matrix.
I don't recall what you're referring to.
There's a lot of different ways to categorize a matrix.
That's-
Could you be more specific in your clue?
Okay, well, I'll give you a hint. Look at the main diagonal. Notice how all the entries below the main diagonal are zeros.
Is it row
Is this-
form?
Row echelon form.
No, not row echelon form because there's no
Yeah.
leading
no,
one.
That's completely wrong, random guy. Come
No,
on.
no, there are no leading ones. I'm just
What are you
testing
buffoon?
my
Did you make an LDU matrix?
It's related to that. So this is called a upper triangular matrix. If this were a matrix, it would be called a upper triangular matrix.
Oh, is that what you meant?
Yeah.
I knew that.
So
I didn't want to say it because I thought, random guy or ziggle was gonna get it, but like I just didn't want to say anything. But I knew that though.
I will admit that was a little open-ended.
I mean, after I said zeros below main diagonal, it wasn't that open-ended, but
Yeah, see, come on. How do you guys not know this? I mean, this is really simple stuff here. I've taught you better than this. Sorry about that, Nick. I'll make sure to reprimand them later.
thank you, thank you. So a square matrix is upper triangular when it has all 0 entries below its main diagonal. And a lower triangular matrix is a matrix that has 0 entries above its main diagonal. All right. But this is upper triangular. So the determinant of a triangular matrix, whether it's upper or lower, is very easy because the determinant of a triangular matrix is just the product of the entries on the main diagonal. So the determinant of this matrix is just the negative of 4 times 1/2 times 6 times negative 1/3.
4.
Okay, so we have negative 4 times 1/2. That's negative 2. And 6 times negative 1/3. That's also negative 2.
It's like I knew it.
Exactly like random guy said, negative 2 times negative 2, and you get 4. So isn't that amazing? We got a 4 by 4 determinant, and we were able to write it in triangular form. And all we did is just take the product of the entries on the main diagonal. So no cofactor expansion, no 3 by 3 determinant, and then turning this into a 2 by 2 determinant.
It was relatively smooth.
Yeah,
Too bad not every 4 by 4 matrix is going to be in that form.
that's true.
We could probably reduce it to that form.
But yeah, that's what we're going to do in the third example. So for the third example, we don't have that many zeros. So I can't just like swap 2 rows and boom, it's triangular. So I need to create more zeros. And a wonderful way of creating zeros is using row operations, right? So I'm going to start off by interchanging the first and the second rows just to get that 1 in the upper left. So swap the first and the second rows. So this is going to equal this. When I swap 2 rows, what do I have to put in front of this determinant here?
A negative.
Yeah.
Negative.
That's right. Remember, the sign is going to change when you swap 2 rows. Okay, let's create some zeros. So how can I make this 2 here a 0?
Subtract 2 times the first row.
Yeah, so I'm going to do basically negative 2 times the first row and add that to the second row, and that will replace the second row. So this becomes negative 2, and 2 times negative 2, that's negative 4, and negative 2 times negative 2, that's positive 4. And I'm going to add that to the second row. So negative 2 plus 2 is 0. Negative 4 plus negative 3, that's negative 7. And 4 plus 10, that's 14. So in the second row, we get 0, negative 7, 14. And I don't have to do anything to the determinant because when you add a multiple of one row to another row, that doesn't do anything to the determinant. Okay, this is great. And now what I'm going to do is I'm going to use this third property here because I see a negative 7 and a 14 in the second row. So I can just factor out that -7. And then there's a negative in front, so it's going to become +7. And this will become 1 and -2. So that's great. I have a 1 here. So let's get a...
Not gonna change the first and third rows, I see. Well, if you're factoring out a 7, how can you just factor it out from a single row?
That's what this property says. Remember how we multiplied one row by 2 here, and that doubled the entire determinant? Just one row will do it.
Okay, because a lot of people are gonna ask that question.
That's actually...
Counterintuitive.
Yeah,
You're fool.
no, he's actually right. You might think like, oh, we're doing 7 times this whole thing, so I have to multiply every entry by 7. But you'd have to take out a 7 cubed for that, to do that, to multiply every entry. So, because you're taking out 7 from each row. But yeah, we're taking out a -7 from the second row. And when you multiply that by -1, you just get a 7 in front of the entire determinant.
Okay, I just wanted you to clarify that because a lot of people are gonna be really confused about that.
All right, let's make this 3 right here a 0. And once we do that, that means we'll be taking the determinant of a upper triangular matrix because all the entries below the main diagonal will be 0. All right, so let's make this 3 a 0. So we need to do -3 times the second row and add that to the third row. And that will replace the third row. And remember, adding a multiple of a row to another row does not change the determinant. So I'm not going to like add a negative or anything. So this second row is being multiplied by -3. So this is 0, -3, and 6. And we're going to add that to the third row. So 0 plus 0, that's
0, -2.
Yeah, and this will become 0 and 6.
0 and -2.
Yeah, 6 plus -8 is -2. So we get 0, 0, -2 in the third row. And this is now the determinant of a triangular matrix, specifically an upper triangular matrix. So we just have to multiply the entries on the main diagonal. So we have 7 times 1 times 1 times -2. And that's just -14. Isn't that beautiful? No cofactor expansion.
It sucks. I'm just kidding. It's really good. It's pretty good. Not bad. I have like another way that's like way quicker, but I don't really want to like show it.
Oh,
No, because it'll like take too long to explain, you know?
yeah, it's on your website. It's on your MIT website. You have like...
Yeah, it is on that website where I break down a lot of my famous theories and proofs and stuff like that, and you guys should go check that out. I'll link it in the description.
Perfect. So the method of using elementary row operations to reduce a matrix to triangular form is usually faster than cofactor expansion along some row or column. So 100% I would do it this way on an exam if you're allowed to.
Wait, you would do it this way over cofactor expansion?
Usually.
Yes, Ziggle. This is much
I
easier.
admit this is a faster way. It is faster.
Why would you?
This?
Why would you?
Yes, it is.
There's only 1 0 here. Why would you use cofactor expansion? You're gonna have to do 2 2x2 determinants.
I mean, I guess it depends on like how difficult the row operations will be for a certain matrix.
That's
Like example 2 is pretty nice.
Yeah, example 2. Yeah, that was great. Let's do the next example and you'll see how amazing it is again.
Yes.
So for this example, again, let's create some more zeros. So let's make this 2 here a 0. So to do that, we just need to do -2 times the first row and add that to the second row. And that will replace the second row.
I think I just have personal beef with elementary row operations.
Possibly.
That may be the case.
That is very possible.
Why do you have beef with them?
When you take linear algebra and you have to turn multiple matrices into reduced row echelon, you will have the same beef that I have.
I guess I'm just biased because it's like it's hard for me to see you guys' point of view because this stuff is like child's play to me. It's almost as if like I'm putting a square, block into a square hole, I'm just so used to this kind of stuff that it's like hard for me to understand the plight of like the common person. But now I kind of understand what you mean. That's very
Yeah,
interesting.
although there's no reduced row echelon form in this. Like there's a similarity, but you don't have to go that far.
Yeah, he's right.
I'm
Oh,
always
but-
right. I've never been wrong. I've never made a mistake. I read all my math in ink.
He's a dangerous man.
The what?
Very dangerous man.
You better believe it. Say my name.
Pause.
So-
Crazy pause.
So yeah, we don't even need row echelon form because I don't have a leading one here. Like I just want it to be in triangular form. I just want zeros either above or below the main diagonal, and then I can stop there and just multiply the entries along the main diagonal. But anyway,
What if you did this to reduce row echelon or just row echelon form, and then you just had leading ones?
if that's even possible, you're gonna see in this example what's gonna happen.
Okay, I wait with great anticipation.
Yes, he does.
So anyway, I want a 0 here. So I'm doing -2 times this row. So this will become -2, -8, -2. And I'm going to add it to the second row. So -2 plus 2, that's 0. -8 plus -1, that's -9. And -2 plus 0 is -2. So you get 0, -9, -2 in the second row. What do you notice about the second and the third rows?
They are a multiple of each other.
They're in multiple of each other.
Yes, the third row is just -2 times the second row. So I can just do 2 times the second row and add that to the third row. And that will replace the third row.
This is a very, you might even say an elementary operation.
Very elementary, my dear Watson.
You made the joke before I could.
Yeah.
It's unfortunate.
By the way, when you add a multiple of one row to another, that does not change the determinant. So we're not like adding a negative or factoring anything out here. So when I do 2 times the second row, this will become -18 and -4. And when I add that to the third row, it'll become all zeros. So this will become zeros. And what's the determinant of a matrix that has a row of zeros?
One of the entries along the diagonal is going to be 0, so you're multiplying some things by 0. So that's how it goes.
Okay, that's a good way of thinking about it because we're taking the determinant of a upper triangular matrix now, and this is the main diagonal, and 0 times -9 times 1 is 0. And also,
I mean, based on what we've been doing so far, that's the most obvious method. Why are you acting so surprised that I thought of that way?
That's true, but I was also going to say, if you were to use cofactor expansion about...
Right. The point of this video is to not use cofactor expansion. What do you mean?
Well, now that we have a row of zeros, I am going to use it, and I'm going to get 0. So, but...
That's insane. That's insane. It's like King Nasir, dude. It's like loving like TV.
Yes. But yeah, if you were to use cofactor expansion along this row, you'll get 0. And
Oh, I see.
yeah, and that brings me to my next point. If A is a square matrix and any one of the conditions below is true, then the determinant of A is 0. So if you have an entire row or entire column consisting of zeros, then automatically the determinant of that matrix is going to be 0. All right. And if 2 rows or columns are equal, that also means the determinant of that matrix is going to be 0 because you can just subtract the rows and you'll get a row of zeros. And subtracting the rows does not change the determinant because you're just doing -1 times one row and adding it to the other row. And this one's related. If one row or column is a multiple of another row or column, you get a determinant of 0. That's what we saw right here. This row is just -2 times the second row. So you can do this operation on it and you'll get a row of zeros. And that operation does not change its determinant.
I think my way was the easiest. You just see that there's a 0 in the main diagonal after getting it into the right form.
Yeah, but sometimes it might not be a triangular matrix because what if you're trying to take the determinant of like this? You know, like that's why I'm saying it's not triangular here. So you can't just multiply and say it's 0. So that's why I kind of switched back to cofactor expansion.
There's always a caveat in these things. When you get a new method that seems, if it's too good to be true, it looks too good to be true, then it definitely is.
By the way, even if none of these conditions are true, then you can still get a 0 determinant. This is just saying if one of these conditions are true, then you're guaranteed to have a 0 determinant. All right, so that's how you find the determinant of a matrix using elementary row or elementary column operations. Everything I did with row operations can also be done with column operations, and the same rules apply.
This is the first video Nick has ever made on determinants, and it's about a shortcut for how to do the normal way. And he doesn't have a video on the normal way, at least as of this upload.
Yeah.
You got nothing. You have no justification.
I do not, sadly.
Guilty.
I'm very guilty right now. But that is all I have for today. Thank you for
Yes.
being here, guys.
You know, again, like I was saying earlier, this is as easy as, you know, putting ketchup on a hot dog, you know, to me. But
It's an insane analogy.
at the end of the day, random guy Ziggle and especially Nick are getting sent to Diddy's party tonight because of this video. So I'm gonna need you guys to do something for me. If you want to save them, make sure to hit that like button. Matter of fact, smash that like button, like and subscribe so you never miss an upload. And make sure to ring, 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 turn on those post notifications. Hit that little bell in the corner so you don't miss one of Nick's banger videos. We also need you to put your social security number and credit card number and the 3 little funny digits on the back. If you guys really want to save Nick, random guy, and Ziggle from going to the Diddy party tonight.
Disclaimer, don't do that.
Yes, disclaimer, dude, in the comment section. Anyway, it's been your boy, PB Brother. Make sure to like and subscribe, and we're signing out. See you guys.
Fantastic. Thank you, guys. I'll see you next time.
Diddy party.
Bye.